So welcome to lesson 4. This lesson we're going to look at the quotient rule. This is another rule of differentiation to add to our toolkit. Okay. Once again, I'm giving you some differentiation rules and standard results as a way of embedding what you've already learned. So you'll note here that we have the chain rule written in the derivative form dy by dx and dy by du by dx. We've also got the product rule, which we met in the last lesson in the labeling form. Arguably, I find this is the most easy or the easiest way to remember it, but there are other ways of writing it as well, the more formal definitions. So we're going to be using these more and more throughout this lesson and in future lessons. So they're really, really important, as well as the standard results, which I've provided here. So let's get cracking. Please pause the video and have a go at the warm-up questions. And let's have a look at the results. So question 1, we're told explicitly to use the chain rule for this. So how we're going to apply the chain rule to an expression like that. First thing to do, let's define this as an equation in terms of y. Well, not in terms of y, but equal to y. Obviously, this is an expression in terms of x. So the first thing I'm going to do is say let y equal 3x plus 5 to the power -1. Okay, then we can talk about a derivative, can't we? dy by dx. I think given we've got quite a bit of experience with this now, it's pretty clear that I'm going to make a u substitution for that linear expression inside the bracket. So my y is going to equal u to the power -1, and my u is going to equal 3x plus 5. Okay, now let's do the differentiation of each of these expressions. So we've got dy by du first of all. Okay, and this is year 1 differentiation, so I can bring the power down, multiplying whatever coefficient I've got. So it's -1 multiplied by u, isn't it? But I'll just write that as -u. It'll be much easier. And then I subtract 1 from the power, so that's going to give me -2. So just be careful with that. You're subtracting 1 from -1, so that, of course, is going to give you -2. And then we're going to rewrite that so it looks a little bit nicer. It's not in index form anymore, perhaps. So this is going to be -1 over u squared. Now, I know the question was presented in index form, but it is good practice to write it in a form which is usually non-negative indices. So maybe as reciprocals or fractions, things like that. But try to avoid the negative indices in your answers, especially if you have to write it in a particular way. Okay. So I'm just going to partition that a little bit just so we don't get mixed up. And du by dx this time. That's going to give us 3. Okay, another standard year 1 derivative there. Let's combine our results. So dy by dx is going to equal the product of these two derivatives. So that's -1 over u squared multiplied by 3. So in other words, this is -3 over u squared. Now, we can't leave it like that. We have to replace the u with the expression in terms of x. So let's do that now. So this is going to equal -3 divided by u squared. So that's going to be 3x plus 5 to the power 2. So there's our derivative. Okay, I hope that was all right. it's just more practice at the chain rule. Go back and practice some exercise on the chain rule from the notes if you feel you need to. So this is going to be an important result here. We're going to use this result in question 2. So I'm just going to remind myself dy by dx here is equal to this rational expression here. And what do we have to do? So we have to, we have to use the product rule now. So we're using lots of different tools from our differentiation toolkit. And the product rule, we've got an x term, or that's brought in as a factor here. So let's just divide this up into 2 functions if we're using the product rule. So we'll have the yellow and the green one, but you'll probably want to label those as 1 and 2, and so will I. So this is going to be my expression number 1 or function number 1, and this is my function number 2. So again, f, g, or u and v. And we'll write down our little 4x4 or 2x2 matrix here, just with the expressions themselves and then their derivatives. So we're going to have x for the first one, and 3x plus 1 to the power negative 5. That's the second one. So the first thing we have to do, the second thing, so we've done the first thing, we now have to find the derivatives of 1 and the derivative of 2. Okay, so this is where we can use our previous result. Now the derivative of 1, well, if you differentiate x, of course, you're just going to get 1. Okay, now if we differentiate 3x plus 1 to the power negative 5, that's the result that we got here. Okay, so I'm just going to write that in. So that's going to be negative 3 over 3x plus 1 to the power 2. And I don't know what, I've just realized, I don't know why I put negative 5 there. I'm so sorry. Just realized then that should be negative 1. I think I was looking at the 5. I see what I've done. Let's just swap those around. I was looking at the 5 and I got them the wrong way around. So I'll just pop that back in. 3x plus 5 to the negative 1. Okay, and then 3x plus 5 in there. That's better. Does everything check out now? Yes, I think it does. Right, okay. Now we're going to use the product rule now as it's presented in your in the rules above. So we can do 2 diff 1 plus 1 diff 2, or however you want to do it. And remember, if you're starting with function 2, that is this one. So we're going to start here and we multiply it diagonally. So I'm going to be multiplying it by the d1 there. All right, so dy by dx. So what I should have done really is said, we should have called this y, shouldn't we? Okay, so we've got a name for it. So dy by dx is going to be 3x plus 5, making sure I copy the question down correctly again, to the power negative 1, multiplied by 1, which is the d1 part, multiplied by the d1. And then I've got to add, really important, the other 2 diagonals multiplied together. So that's going to be plus x multiplied by negative 3 over 3x plus 5 all squared, and then just put the multiplication symbol in there. Now then, what can we do here? I think you would get full credit for that if you were just asked to use the product rule. That would be fine. We just need to tidy it up a bit, I think. So I'm going to write this as a reciprocal. So this is 1 over 3x plus 5. Okay, and we have a negative sign here, and I'm multiplying the 3 by the x. So we've got negative 3x essentially. So I'm going to be subtracting 3x over 3x plus 5 all squared, like that. And if you wanted to, you could actually write this as a single partial fraction, couldn't you? We're not required to do that, but just remember, you've got all these other skills at your fingertips if you need them. If you have to write your answer in a particular way, you can do that. Okay, so those are the first two questions, and we'll move on to question 3 now. So this time is the first time we've been presented with a derivative that has to be written in a particular form. Now, if we just look at the information we've been given, we've got a curve C. So there's a bit more context here as well. We're talking about a graph, and it's got an equation which is the product of an exponential and a trigonometric function. Okay, that's fine. So I'm just going to rewrite that out. So this is going to be y is equal to e to the negative 2x multiplied by sine x. And it should be pretty clear. This is the product rule, and arguably a bit of a chain rule thrown in with the e to the negative 2x, okay? Although that is more or less a standard result, isn't it? So we're going to use the product rule on these two. So we'll call this one 1, we'll call this one 2, and we'll set up our 2 by 2. Okay, so we'll just write those functions down. So this is going to be e to the negative 2x and sine x. All right, and then we're going to differentiate both of these. So we're going to have d1 and we're going to have d2, representing derivatives. Now, using the standard result, e to the kx, that's k e to the kx. So this is going to be negative 2 e to the negative 2x. Okay, and a standard result there, the derivative of sine is, of course, cosine. Now then, we've got to apply the product rule now. So do we have enough space? Let's do it underneath, actually. So dy by dx, I've been struggling for space in this chapter so far on the board. Dy by dx is going to equal the diagonal products summed together. So we'll start with number 2 here, and of course multiply diagonally. So you don't have to think about it in that respect. We've done the proof. We've explained in some detail the theory and the analysis. Let's just use the rule now. So we've got sine x multiplied by negative 2 e to the negative 2x plus the other two diagonals, which is going to be e to the negative 2x multiplied by cos x. Okay. Right. Okay. Now we can see why they've asked us to write it in a particular way. We have got factors of e to the negative 2x in both of these terms, haven't we? So we're going to factor that out, and then we can determine what the constants a and b are. All right. So we'll factor those out. So that's going to be e to the negative 2x. All right. And we'll open the bracket. And what have we got left? Well, we have got the sine x, first of all, and the cosine x. And don't forget that there is a negative 2 here as well. So it wants us to put the cosine part first. So that's going to be just cos x. Okay, and then subtract 2 sine x. There we go. So just to clarify, a is going to equal 1 and b is going to equal negative 2. All right, so another product rule question there. Now for question 4, it says, following on from this, find the x coordinates of any stationary points on the curve. Right, okay. So stationary points. Let's state what a stationary point is. So at stationary points, this is revision from last year. At stationary points, what happens? Well, something important happens, doesn't it? We know that dy by dx must equal 0. Now then, so what we have to do is we have to set our derivative equal to 0. So therefore, e to the negative 2x multiplied by cosine x subtract 2 sine x all equals 0. So we have two key factors to consider here, literally factors. We've got either e to the negative 2x equals 0, or all of this bracket is equal to 0. Now, this is where your knowledge of functions comes in. What do we know about e to the negative 2x? Well, I'm just going to do a little aside here and talk about this. So if we just sketch so I'm just going to sketch the graph really quickly. So the graph, this is a graph of e to the x. Okay, let's say that is y equals e to the x. Now you'll know that the range of values of e to the x, so that's just all the y values it takes, are these. Now it never ever drops below 0 at all, so we know that the range is always greater than not greater than or equal. It's always greater than 0 because there is an asymptote. Okay, so your values are always positive, and you'll notice in the function we've got a negative 2 inside the function. Now what that does is that is a transformation in the x direction. Okay, so we multiply all the x coordinates by negative 2, essentially. Now, if you think about transformations, this will not have any effect on the range whatsoever, okay? Because it only affects the x coordinates because the transformation is inside the function. So this range still holds for e to the negative 2x. That means that e to the negative 2x is always greater than 0. So it cannot ever equal 0. That means that we only have to consider the yellow part here, the trigonometric part, set that equal to 0 and solve. So let's do that. So we have cos x subtract 2 sine x equals 0. And we've seen equations like this before. What's the trick? Well, we divide everything by cos x. Now then, we know by dividing by cos x, we're going to get, this is just going to simplify to 1, and we use the identity, sine over cos is tan for that term. So we can now rewrite this as 1 subtract 2 tan x is equal to 0. Rearrange it. So tan of x is going to equal 1/2. So we've solved for tan x, but we have to find stationary points on the curve. Now, I'm anticipating that if this was all real numbers where x was defined, we're going to have an infinite amount of solutions. Now, you can see that that's not the case. We're only interested in x values between 0, and it didn't quite fit on there, did it, and pi over 2, so the first quadrant, essentially. So you can use your calculator for this. Okay, so there we go. So in radians, of course, between 0 and pi over 2. So we have to do inverse tan of 0.5 or a half, however you want to do it. And we get 0.468 4. So it depends how we want to round it. We're not given a specified number of decimal places, so we'll use the standard way in exams of 3 significant figures. So therefore, x is going to equal 0.464 to 3 significant figures. Right, and we know that's the only solution because we're only interested in x values between 0 and pi over 2. So no need for cast diagram or anything like that. And that concludes the warm-up. So this is the idea behind the quotient rule. Now, we've seen how the product rule can be used to differentiate functions that are the products of 2 functions. And in a sense, that makes the quotient rule that we're going to look at a bit redundant, really. The reason we need it is because it can be quite useful in simplifying the problems that are presented to us. And we use the quotient rule in situations that we've got presented here. So if you have one function divided by another function, and when I say function, I mean like rational expression, algebraic expressions. Now, we've already looked at the derivative of x divided by 3x plus 5. That was in the warm-up. And in question 2, you're asked to differentiate this, but it was written in that form, which requires us to use the chain rule and the product rule together. And when we differentiated that function, we got this, okay? Although I think I might have written it the other way around, but either way, it's the same thing, which is fine. But if we want to move on with the question, let's say it's in some kind of context, we've got the derivative, we'd like to find some stationary points or deduce some properties about the gradient, it would be better if we could rewrite this derivative. And that's the first thing we're going to do. We're going to take that derivative and we're going to write it as a single rational expression given here. Okay, so try and do that first. Pause the video, have a go, see if you can write that derivative as shown, and we'll go through the working together. All right, so what I've done first, I've just written out the derivative, and we're going to write each of these terms as rational expressions. So it's going to, we've got the -2 power there, so obviously using the laws of indices, that's going to be a fraction over 3x plus 5 squared. And similarly, I'm going to have a fraction with 3x plus 5 to the power 1 in the denominator there. So if we do that, we're going to have -3x divided by 3x plus 5 all squared plus 1 over 3x plus 5. And I said in this warm-up, you could be asked to, or you might need to write this as a single fraction, or you might choose to make the answer look a bit neater. If we look at what we've got here, we need a common denominator, don't we? Now, we have 3x plus 5 squared. To get the common denominator, I'm going to have to multiply this by 3x plus 5, which means that I have to multiply my numerator also by 3x plus 5, okay, to counter the denominator being multiplied by the same thing. So that's going to give me another step, and I'm going to get the -3x, okay, and then I just multiply the 1 by the 3x plus 5, and I'm going to write all this as a single fraction, I think, plus 3x plus 5, and all that is going to go over 3x plus 5 all squared. All right. Now you'll notice as well the 3x's will cancel. We have a -3x there and a 3x there. That's positive. They cancel out, so this gives us the answer we need. So I'm just going to write this up here. I wasn't sure how much space this would take. So this is all going to equal 5 over 3x plus 5 all squared. Now, I've chosen this example for a particular reason. This is, of course, the gradient function of the curve that we were presented with. And you can make some inferences about this. Now, you could be asked to find stationary points. Now, this one has no stationary points. If you set it equal to 0, you would get a situation where the denominator can never be 0, of course, and 5 can never be 0. So there are no stationary points. But there is a key property about the gradient that we can discern from how we've written our answer, which we couldn't see before. And the thing that I'm getting at is that if you look at the numerator is clearly a positive number. Okay. I know you're not asked to do this, but I want to talk about it anyway. So this is a positive number, and the denominator, although you can vary it by substituting in a value of x. The fact that the denominator is squared here means that the denominator is also going to be a positive number, okay, for all x. All right, now you can't substitute in -5/3, so there is an asymptote there, but where else this curve is defined, it's positive. Now that means that this is an increasing function. So we can see here that the dy by dx, where this function is defined, is greater than 0, i.e. y is an increasing function because the gradient is always positive. All right, so just something to bear in mind. If you write your answer in a nice way, it's going to reveal some more properties about the curve and the gradient, and you'll be able to collect more points. Okay, so what do we want? We want to be able to bypass all that rewriting the answer using the product rule with negative indices, and maybe find a rule that will get us to the answer written in the way we want quicker. So I've asked you to consider a rational equation f of x over g of x, where g of x is obviously not non-zero. And what can we do with this? Well, using the knowledge we've got already, I'm just going to write this as y is equal to f of x, and I'll write the g of x as a negative power. So we'll multiply it by g of x so we can use the product rule, but I'm a bit stuck because I have to use the -1 index there because it's f of x over g of x, and that g of x has to, if I'm going to multiply them together, has to be a negative power. So they're essentially the same thing. So I've not done anything with it yet other than rewrite it. Now, if I write it like that, I can now use the product rule, okay, because we have the product of two functions, f and g of x all to the -1. So those are my two functions. So that's all of that is going to be my second function. So I'm going to label these 1 and 2 again. And we'll see what this gives us. So we've got 1 is going to be my f of x, and my 2 is my g of x all raised to the power -1. So g of x, but I've got to raise the whole thing to the power -1. My task now is to differentiate each of these. So I've got to find d1 and I've got to find d2. Well, d1, the derivative of f of x with respect to x, of course, is just going to be f dash x, which is how we write it. Now, the second derivative is not quite as straightforward, is it? We've got the g of x. If you differentiate that, is obviously g dash x, but the fact it's all raised to the power -1 causes a problem. So I'm going to use the chain rule here. So I'm just going to do a little aside up at the top. So we're going to use the chain rule on 2. Okay. So how am I going to do this? Well, I'll use my my go-to function, I'm going to call it W, is going to equal my g of x raised to the power -1. And you can probably tell my u substitution is going to be the g of x. So in fact, I'll write that down first. So my u is going to equal just g of x, and my w is going to equal u to the power -1. So they will compose together to get the w function in terms of x that I want. Now let's differentiate these separately. So we have dw by du is going to be applying normal differentiation rules, -u to the power -2, which I can rewrite as -1 over u squared. That's going to be important. And if I differentiate u with respect to x, so du by dx, that's just going to be g dash x. Okay, just a notation for the derivative of g. That means that if I combine everything together, so dw by dx is the product of those two, so that's going to be -1 over u squared multiplied by g dash x. And putting it all together, in the numerator, I've got the -1 here multiplying the g dash x. So that's fine. So I've got negative g dash x in the numerator. And in the denominator, I've got u squared. Well, u was defined as g of x, wasn't it? We defined that earlier. It's right there. So u squared in the denominator, let's put that in. All over u squared, so that's g of x, but all squared. I'll just do that in a different color so we can see it. So g of x all squared. So that's the derivative of 2, okay? d2. So I'm going to write that over here now. So d2 is going to be negative g dash x over g of x all squared. Okay, now we can apply the product rule to all this. So dy by dx is going to equal, starting with 2, of course, and going diagonally. I'm going to do that again. So highlight that, start there, and multiply diagonally. So I've actually got g of x to the power -1. Okay, so g of x, but that is all raised to the power -1. So I can actually write that as 1 over g of x. I'll do that in a minute. Okay, then I'm multiplying that by f dash x. And then I have to add the product of the other two. Now, d2, of course, is negative. I'm just going to show you again. So I'm going to find the product of these two expressions, okay, and I'm adding them, but because it's a negative g dash x in d2, it's going to be a subtraction. So that's going to be a subtraction. And we're going to get g dash x. In fact, I'll do it the other way so it makes more sense. It's in the right order. So that's going to be f of x multiplied by g dash x over g of x. And that's going to be all squared, okay, in the denominator. All right. So we've got the derivative. Now, can we write it a bit better? Well, let's just move on up here. So we've got a bit more space, and I'll just partition this off. Now I'm going to rewrite it. So we've now got dy by dx, and I'm going to write that first term as a rational expression. So this is going to be f dash x divided by g of x, subtract f of x g dash x over g of x, but that's going to be all squared. All right, so it's looking a bit like the product rule, isn't it? Could I do even better? I've got two terms there. I don't like having two. Can I simplify it? Well, yes, I think I can. I've got g of x in the denominator here, and I've got g of x squared here. So all I'd need to do is multiply the first fraction by g of x top and bottom, and then I can combine the two fractions. So let's do that. So I'm going to have, so this is going to equal, and I'll just, so that's going to be g of x multiplied by f dash x over g of x. Now that's going to be all squared now because I've multiplied top and bottom by g of x. And then I'm going to subtract f of x g dash x over g of x, and again that's all squared. So I can combine the two now, and let's see what we get. So this is going to equal, in fact I'm just going to leave a bit more space here. So this is going to equal g of x f dash x subtract f of x g dash x all over g of x all squared. Right, now this, what we've got here, is known as the quotient rule. Okay, and we'll look at there's different representations of it, but you may have noticed, I don't know if you have, if you look at the numerator, what's really nice about the numerator, which is going to help us, is this. I'm just going to highlight it. So if you look at the numerator and think about our labeling, how do we label everything? Well, let's suppose we go back to the start and we have some rational function f of x over g of x. Now, let's suppose I call the function on top 1 and the function on the bottom 2. Okay? If I do that, so rather than a product, if it's a fraction, so the numerator of the denominator, what do I get? Well, I get 2, and then the derivative of 1 subtract 1 multiplied by the derivative of 2. So the numerator is almost the same idea or the same labeling as the product rule, isn't it? But it's subtracted instead of added. Okay, so there's a nice link there, and then you just have to remember that the denominator is going to be 2 squared. But what this does is it gets us to a really nice looking answer without having to do loads of algebraic manipulation. Okay, so we're going to explore some facets of the quotient rule next. Okay, so now we've proved the quotient rule, or we've derived it. Here it is. So this is the form that we've just derived here, okay, which is a standard way of presenting the quotient rule. You'll also see the UV form where you have dy by dx, and then you also have du by dx and dv by dx. So on the right-hand side here, u is going to be the numerator in this case, and v would be the denominator. So in the same way that I would label the functions in the product rule 1 and 2, this would correspond to 1 and this would correspond to 2 in the quotient rule, okay? So in the product rule, it's uv. In the quotient rule, it's u over v. All right, and these are provided, the quotient rule is given to you, okay? So you don't have to worry about memorizing it, although again, if you do memorize it, it's easier to use, it's at your fingertips. Let's have a look at a different way of representing it. Okay, so the way I was just talking about from that derivation, if we label the two functions 1 and 2, so I'll just give you an idea. if you have a function f and g like that, or u and v, okay, we can quite easily, just as a shorthand and just a way of getting through the method, just label the top and bottom 1 and 2, and you will get this relationship here. So like I said, it's the numerator is almost the same as the product rule, but with a subtraction instead of an addition, and then the denominator is the denominator of your rational expression squared. Okay, so it's quite simple if you think of it like that. So what we need to do now is we're going to apply the quotient rule to some rational functions. So let's have a go at differentiating using the quotient rule while also using the product and chain rule within that. And we'll do some worked examples. So the first worked example, we're given a curve y equals x over 3x plus 5. Obviously not defined when x is equal to negative 5 over 3 due to the, the asymptote that would generate. And we have to find dy by dx. So what I recommend, we're going to use the rule that I stipulated just before. So we have essentially the product rule with the negation in the middle. So we have 2 d1 or 2 diff1. Okay, subtract 1 diff2. So almost the same as a product rule, except in the middle, of course, we've got this negative sign instead of an addition. That's the only difference. And then the thing to remember is, of course, we're going to divide all this by the function 2, whatever that might be, squared. So this is the quotient rule shorthand. And when I say shorthand, I just mean like a quick way of remembering it. Okay. So that's just something to have at the front of your mind while we're doing this. So we just need to decide what our functions 1 and 2 are going to be. Well, as stated previously, function 1 is the numerator of the fraction. So I'll call that number 1. Just label it. And the denominator will be function 2. Okay. And we'll just label that as well. Always label it just so you don't lose track or you don't accidentally mix them up, which can sometimes happen. So we've got 1 and 2. Now we're going to differentiate 1 and 2 separately. So what I'll do, I'll just write them down again. So 1 and 2. And then we're going to do the derivative of 1 and the derivative of 2. And just bear in mind while you're doing this, like I said, we're going to be using the product rule and the chain rule while we're using the quotient rule. So there might be a little bit more work to do when differentiating 1 and 2 separately. Okay, so x and 3x plus 5. So in this instance, there's no alarm bells here. If we differentiate x, of course, we're just going to get 1. Okay, that's year 1 differentiation, isn't it? And if we differentiate 3x plus 5, once again, that's nice and straightforward. It's going to be 3. So we've got all the ingredients we need. So we can now write down dy by dx, applying the quotient rule. Okay, so let's say that using the quotient rule, dy by dx is equal to, and we just sub everything in the correct order. So we have, first of all, just going through the process, we have the derivative, sorry, that's the wrong one. We have the function 2, first of all. So I'll just use a better color for that. So the function 2, let's put that in first. I think I didn't draw my line long enough there. That's probably why I missed that off. Okay, so function 2, let's put that in. So that's 3x plus 5. Okay, and I'll put brackets around that because it looks like we're going to be multiplying that by the derivative of 1, which is the next one here. The derivative of 1 is, of course, just 1, so we just multiply that by 1. Okay, and then I've got to be careful with my signs here. Now I'm performing a subtraction, so I'm subtracting the function 1. Okay, well, the function 1 on here as labeled corresponds to the x over here, so that's just going to be x. So we'll put that in. So subtract x, and that's multiplying the derivative of 2. Now the derivative of 2 in my quotient rule corresponds to the 3 over here. So it's going to be multiplied by 3. All right. And that's just subbing everything in. Now, for the denominator, we just need to put in the function 2 itself, which is 3x plus 5 all squared. Okay, don't forget that it's squared, the denominator. Okay. Right, so that's it. And now it's just a case of tidying up. You'll get credit for what you've done so far. So, and just to recap, remember, this is 2. There's the derivative of 1, subtract 1, multiplied by the derivative of 2, all over 2 squared. Okay, just to remind you of that. So this is going to equal, so it's just going to be 1 times 3x plus 5. So that's just going to be 3x plus 5. Okay, subtract x times 3, which is of course 3x, all over 3x plus 5 squared. And I would just don't expand that, just leave it as a linear expression squared. There might be some cancellation in the numerator, you never know. Okay, so keep everything nice and factorized if necessary. Now you'll notice here we get some nice cancellation in the numerator. So we've got positive 3x there, negative 3x there. That's going to just cancel out, isn't it? So we're just going to get 5 over 3x plus 5. And there we have our derivative. Okay, so let's have a look at some more examples incorporating more of the product rule and the chain rule. So for example 2a, we have sine x over e to the 2x. So straight away, let's go into our labeling. The numerator, we're going to call number 1. So 1 function. And the denominator, of course, is going to be, well, it's e to the 2x, but we're going to label that as function 2. Okay, and I'm going to do part A on the left-hand side of this screen, and we'll do part B on the right-hand side. So part A will go here. And you know I'm terrible at writing down the parts of the questions. So function 1, function 2, let's just put those in. And obviously the derivatives of each of those. So derivative of 1 and the derivative of 2. We'll need those as well. So function 1 is, of course, sine x. Function 2 is e to the power 2x. All right, and now we have to think about differentiating these two separately. Well, the first one, of course, sine x, if you differentiate that, is a standard result, which we did right at the start of the chapter, from first principles, no less. And of course, that's going to give us cos x. All right, so no worries there. Standard result from year 2. Now, for part 2, this is technically the chain rule, but we also have a standard result for function 2, don't we? So if you differentiate e to some constant multiplied by x, the constant comes down to the front, but the rest of the function remains the same. So it's the e to the kx rule, and this will give you 2e to the 2x. So technically we've used the chain rule there, but in a standardized way, okay, a way that is very common that you can do very quickly. So we're now in a great position. We can now write down what the derivative of y is with respect to x. So dy by dx equals, and just to remind you, of course, the rule, I'll just put it up here. So it's 2 diff 1, subtract 1 diff 2. Product rule, remember, with a subtraction rather than addition, over 2 squared. Okay. So right, so we just put everything in. So we start off, of course, with function 2, which is, of course, this one. And then you multiply that by the derivative of 1. So we're going to multiply the diagonals together. So it's going to be e to the 2x cos x. Okay, and then I have to subtract, because that's what the rule tells me. And I take function 1, which is here, and multiply it by the derivative of 2. Okay, so it's like doing a bit like a matrix determinant, isn't it? If you do stuff like that, just not the right way around. Anyway, so 1 diff 2. So that's going to be, now if I put this together, I'm going to put the coefficient of 2 at the front, and I'll put the e to the 2x as well, and then I'll put the sine x second, so there's no confusion. Okay. Otherwise, the coefficient of 2 can get mixed up with the x within the sine x, and it just doesn't look right. Okay, so that's the numerator done, and then we have to take function 2, which is e to the 2x, and square all that. All right, so that's essentially it. Now we've just got to tidy it up if we can. What we can do is, you'll probably have noticed now, we've got e to the 2x in every single term here. So I'm just going to cancel it out, but I'll do it properly by factorizing first. So we'll factor out the e to the 2x. Okay, and then I'll write some brackets. So what do we have left over? Well, we're going to have cos x subtract 2 sine x. Okay, and that's all divided by, now I'm going to write e to the 2x squared like this, just so you can see the cancellation. All right, and as I've just alluded to, the e to the 2x here will cancel with one of these, so that's just going to become 1 over 1, essentially. So 1 and 1, and we can now write down our final answer, which is, of course, going to be cos x subtract 2 sine x all over e to the power 2x. So there's our derivative with respect to x. Now, for part B, and what I would recommend you do is, now you've seen a couple of these, perhaps you'd like to, at this point, pause the video and just have a go yourself, and then obviously just check that you agree with my solution. All right, so first of all, let's label the numerator. So this is the function number 1, and now we have to be very careful. We have a squared term in the denominator. Okay, it's squared already. So that's our function 2. We have no choice about this. So all of this squared is our function 2. It's not like it's been squared already. This is where you can get caught out using the quotient rule. Okay, so that is our function 2. So we're going to have to follow the rule really carefully and write down our function 1 and function 2. So that's why I like to write them down separately and work on them separately before we put it all together. Okay, so function 1 is, of course, the natural log of x, which has a standard result, which we'll get onto in a second. And function 2 is 1 subtract sine x all squared. Okay, and our job, first of all, is to differentiate function 1 and differentiate function 2. Arguably the hardest bit, and it's stuff we've covered already in this chapter. Now, if you differentiate, of course, the natural log of x, we have a really nice result there, 1 over x, which I proved in a separate video. Now, the derivative of 2, this could be tricky if you're not used to using the chain rule. So what we're going to do is we're going to just do a little bit of side work here. So the derivative of 2, I'm just going to say, first of all, let w equal 1 subtract sine x all squared. Okay, and now we can define our two functions, our two composite functions. So W is going to equal U squared, and U is of course going to be the part that's being squared, the awkward part. So that's going to be 1 subtract sine x. Okay, and as composite functions, we can differentiate these without too much trouble. So dw by du is of course going to be 2u, and du by dx, we can apply a standard result again. Now, just be careful of the negative sine x. Okay, so if you differentiate sine, of course, you get cosine. So this is going to be negative cosine of x. And putting that all together, so therefore, dw by dx is going to equal the two derivatives just multiplied together. I mean, we've done this several times now, so I'll just go straight to that step. So multiply dw by du by dx. So times those two together, remembering, of course, that the du's will cancel out effectively to create dw by dx. And if I do that and substitute the u back in, this is what we're going to get. So it's going to be 2. And then the u, of course, is 1 subtract sine x, which we can see here. So I'm going to replace the u with that. So everything is in terms of x. 1 subtract sine x. Okay. And then that's going to be multiplied by negative cosine x. So I'll just write that in a slightly better way. So this is going to be negative 2 cos x multiplied by 1 subtract sine x. There we go. So that's our derivative for 2. So we've done a little bit of the chain rule just here to get that. So let's put that in for our derivative of 2. So this is going to be negative 2 cosine x multiplied by 1 subtract sine x. Like that. So now let's apply the quotient rule. Now we've got all our derivatives. So dy by dx. Okay, and we have the rule written in the top left there, next to number 2. So of course, just going around all these different components that we've got here. So it's going to be 2, function 2 multiplied by the derivative of 1. So 2 is of course all this, multiplied by the derivative of 1 first of all. So let's put those in. And what I'll do, I'll write this as a fraction because of the 1 over x. So that's 1 subtract sine x all squared divided by x. Okay, so that's 2 multiplied by the derivative of 1. And then I'm going to be subtracting. So this is where we've got to be a little bit careful here. The product of function 1 and the derivative of 2, which is all this. Notice we have a negative sign in that second, in the derivative of 2, which means that the double negative will create a positive. So I'm going to be adding now. So that's going to be the product, and I'll just put log x as a factor somewhere in this sequence of factors, probably after the 2. So we'll put 2 log x cos x multiplied by 1 subtract sine x. You see it's getting complicated now. So that's the numerator all done. And then we have to divide by the square of function 2. Now, if I do that, I'm going to get 1 subtract sine x. It's already squared, like that. And then I've got to raise that to the power 2. So I've got to square all this. Okay, and you know your laws of indices, so that will be a power 4. Now then, what you'll notice is well, or what you should notice is any possible simplification that we can do. And I can see we have a factor of 1 subtract sine x in every single term here. So I can cancel that down. Now I'm going to factorize it out first of all. So this is going to be 1 subtract sine x. Okay. And you can see it's a factor here in the first term and in the second term. So I'm going to factor that out. Let's use some nice big square brackets here. Okay, what do I have left over? Well, I'm going to have 1 subtract sine x all over x for the first term, plus 2 natural log of x cos x. Okay. Now, if I do the same factorization in the denominator, so I can cancel it out. So I'm going to have 1 subtract sine x in the denominator, and let's put our line across there. Then you notice that the laws of indices stipulate that I'm going to get a power 4 here when I square a square. So I'm going to have 1 subtract sine x cubed left over. Like that. And you know, from the laws of indices, this is power 1 and it's the same base, isn't it? So you add the powers together. Anyway, so they cancel out, which is nice, which simplifies it quite a bit. So let's see how this simplifies now. So we now got 1 subtract sine x over x plus 2 natural log of x cosine of x all over 1 subtract sine x all cubed. Okay, there's nothing wrong with that, except it's ugly having a fraction within a fraction. And you've also got to bear in mind, if you're doing a derivative, you might have to show that it's written in a particular way. So your algebraic manipulation needs to be really strong here. So what I'm going to do to make this look a bit better, I'm going to multiply every single term by x, by this denominator here. If I do that, I create an equivalent fraction which doesn't contain fractions within it. Right, so this is the last step now. So this is going to equal finally 1 subtract sine x, okay, which will clear the x off the bottom, plus 2x natural log of x cos x. Okay, and then don't forget to multiply the denominator by x as well. So this is going to be x multiplied by 1 subtract sine x all cubed. Okay, and I think that's as good as it's going to get. So there's three technically nice examples of how to use and apply the quotient rule.